Hello, welcome to the IPv4 class. To have a firm understanding of IP version 4, we need to understand conversion very well. What are we going to convert? We are going to learn how to convert from binary to decimal and vice versa. So we'll convert from binary to decimal and from decimals to binary. What is a binary numeral? A binary numeral is a number to the base 2. So any number in the binary is less than 2. So you can either have a 0 or a 1. No number is more than 1. A number to the base 2, below 2. Decimals are also numbers to the base 10. So starting from 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. That is the maximum number you can have in a decimal numeral. So to help us convert from binary to decimal, we are going to use the chart above here. It will be in our interest to memorize them. So let's go. 1 plus 1 will give us 2. 2 plus 2, 4. 4 plus 4, 8. 8 plus 8, 16. 32. 32 plus 32 will give us 64. And 128. So in that way, we can memorize the charts above. So let's take an example. Supposing you are given a binary numeral of... No, let's start from decimal to binary. So if you have a decimal numeral of 178, and you've been asked to convert it to binary, what do? You are going to decompose, break this number down, 178. So if you break this down, you are going to have components. This is one way of breaking 178 down. 100 plus 70 plus 5 and plus 3. We have broken it down. By these members, none of them are members of the chart above here. So this is not a proper way of breaking 178 down. The best way to break 178 down is to do so whilst you have all the components as members of the chart we are seeing here. So that's the proper way in which we can break 178 down. So let's go by the subtraction rule. From the chart here, which number is the next lower to 178? We can see 128 is the next lower. So you are going to subtract 128 from 178. That will give us 50. 50. What is the next lower number from the chart? It is not 64. 64 is higher than 50. So the next lower number is 32. Mark 32 here. So you're going to subtract 32 from 50. And that will give us 18. 18 is not in the chart. So we move on further to break it down. Which number is the next lower to 18? It is 16. So subtract 16 from 18. 16 from 18. And that will give us 2. 2 is in the chart, so we end there. 2 is here, so we end there. So all the numbers that we have asterisk under, we are going to mark 1 under them. 1, 1, and 1. The rest becomes 0, 4, 10 to 0, 8, 0, and 64, 0. So breaking 178 down to binary, we have 1, 0, 1, 1, 0, 0, 1, 0. 1, 0, 1, 1, 0, 0, 1, 0. That is how you can break 178 down into binary. Let's take another example. Let's see how we can break 119. How can we convert it into binary? So we are still going by the subtraction rule. Which number is next lower to 119? It is not 128. It is 64. So you are going to subtract 64 from 119. And that will give us 5 and 5. 55. 55 is not in the table here. So the next lower number to 55 is 32. You bring your asterisk here. So subtract from 32, and that will give us 3 and 2. 23, the next lower number is 16. Mark it, mark under, so that you don't forget. So you are subtracting 16 from 23, and that will give us 7. 7, the next lower number, it is not 8, it's 4. So 7 take away 4 will give us 3. We are still breaking it down because 3 is not in the chart here. 3, the next lower number is 2. So you subtract 2 and you have 1. 1 is here, so you turn it on. So we are going to mark 1 under all the asterisks and 0 under the ones with no asterisk. So 119 into binary is 0111 0111. Very simple steps in converting from decimal to binary. Let's do the vice versa. So how can we convert from binary to decimal? We are going to go by the addition rule. So an example is converting from 11101. Convert this binary to decimal. So we have 8 digits here. 1 1 1 1 2 3 4 5 6 7 8. So each digit here has a member up here. So this one represents 128. This one here represents 64. This 32. The 0 is for the 16, and 4 1. So 1 2 3 4. So we have 1 under 128. We are going to add 128 plus 64 is on. If you see 1, it means off. 0 means 1 is on. 0 means off. So 64 has 1 under 8. So 64 is on. 32 has 1 under 8. So 32 is on. You're adding. Plus 16 has a 0. So 16 is off. You're not going to add 16. 8 has a 1 under 8, so you add 8, plus 4 has a 1, add 4. 2 plus 1. So adding it up, 2, 1, 4 is 7, 7 to 8, 15. That will give us 2, 2, 4 plus 15, 9. 2, 3. So converting 1110 1111 to decimal will give us 239. So the point here is, if you have a decimal numeral, it will represent 8 digits in binary. 8 digits in binary. For every decimal numeral, you can have 8 digits in binary. Please note this point as we're going to use it in our IPv4 calculations. Please, let's take another example. Supposing you are given all ones, 1, 2, 3, 4, 5, 6, 7, 8, all ones, and you are asked to convert to decimal. So this one here is for the 128, this 64. In fact, we have all ones, so let's mark 1 under every digit here. Every number is turned on. So we are going to add everything, 128 plus 64 plus 32 plus 16, 8, 4, 2, and 1. That will give us a total of 255. So when we have all ones in binary, the decimal equivalent is 255. Let's take one last example. So let's give ourselves 0, 0, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8. This 0 is for 128. This is for the 64. 132 is turned on. 16 is off. 8, 4 are all on. 2 and 1 off. So addition, we are going to add 32 because it has 1 under it and it's turned on. So 32 plus 8 and plus 4. 4 and 8 will give us 12, 44. So this number in decimal is 44. So again, for a decimal numeral, we have 8 digits in binary. That is a point worth noting. With this in mind, let's come to our main topic, IP addressing. IP addressing. IP stands for Internet Protocol. So the key word here is address. What is an address? Addresses are used for identification. So we have several types of addresses. We can mention one, the postal address. Our names are even forms of addresses. Our telephone numbers are also forms of addresses. So one unique features about addresses are always derived from something. How do I mean? So if you have a name, for instance, my name is Chofo Nathaniel. Chofo Nathaniel. This Chofo is my surname or my family name. Nathaniel identifies me within the family. The Chofo is a constant. It always repeats itself. So as long as you come from that family, you will be called Chofo. So we have Chofo Samuel, Chofo Mavis, Chofo Regina, Chofo Sarah, and so on and so forth. That tells us that the Chofo is a constant, but the rest can be anything. These are features of addresses. Another example is the telephone numbers. So let's use telephone numbers to identify the feature of addresses. My telephone number is 024 and 4 30 34 60. we can see that this number was derived from something, 024. Anybody who knows the code, this 024 code, will know that my number was derived from the MTN network. Any other person who subscribes to MTN will obviously have a code of 024, then the rest will follow. So this 024 identified the network that this number was derived from. So every address was derived from something. Same way, IP addresses are also derived from something. IP addresses are derived from networks, network IDs. So what is a network? The simple way I can describe a network is to design a network. So if you have a router here, this is a symbol for routers, just a 0 and 2 crosses. And you connect a cable to a switch, you have created a network. This is a network. On this switch, you can connect your computers. So that's a network. All these computers fall within this network. So if they are to be given IP addresses, then the addresses should be derived from a network ID, as in Chofo Nathaniel, Chofo Sarah. So let's assume we have a network ID of 192.168.30.0 and a /24. I will explain the /24 later. 192.168.30 is a constant, as in Chofo. It will always repeat itself for every address within this network. But the number here can be anything. So if you want to assign an IP address to this PC, 192.168.30.1. This PC will also have an IP address of 192.168.30.2. 192.168.30.3.4.5 and so on and so forth. This is a constant. So this address has been derived from the network ID that you are seeing here. So at least we have a picture of what IP addresses are. With this in mind, let's step a little deeper. So a typical example of an IP address is 192.168.48.20. All these numbers are in decimals. Computers are comfortable with binary, whilst humans are comfortable with decimals. So let's convert these numbers here to binary, each one of them. Converting 192 to binary, we have 1, 1, 2, 3, 4, 5, 6. 8 digits. One decimal numeral represents 8 digits in binary. Dot 168 will be, this will be on. This will be on 160, and that. The rest will go off. So 168 will give us 1 0 1 0 1, 3 zeros in binary. What about 48? 48. So this number goes on, and this one goes on. the rest are off. 32 plus 16 will give us 48. So we have 0, 0, 1, 1, 4 zeros, representing 48. How about the 20? $20 will be 16 and 4. The rest go off. So the 20 is 0, 0, 0, 1, 0, 1, and 0, 0. So we've converted the above IP address to binary. This is how the computer will see the IP address above. What is a bit? B-I-T. A bit is either a 0 or a 1. So if I have 1, 2, 3, 4, 5, 6, how many bits do I have here? 5 bits. What about 1, 2, 3, 4, 5, 6, 7, 8? How many bits? 8 bits. So in the above, how many bits can we count here? 8 plus another 8 plus another 8 and 8. So 8 bits here, 8, 8 and 8, adding up to 32. So IP addresses are 32-bit addressing system, IPv4. The longest length you can have is 32-bit. Every IP address is a 32-bit address system. This part here is called the first octet. This part is the second octet, third octet, and the fourth octet. So first octet, second, third, and fourth octet. So the 32 bits are divided into 4 equal parts. Each octet has 8 bits in it. So that's a point that we have to take note of. Yes, so this is an IP address. Now, as we said earlier on, IP address comprises of the network bit and the host bit, adding up to 32. So if you count all these 32 bits here, part of it belongs to the network and part belongs to the host. As in Choffle Nathaniel, Choffle is the network portion and Nathaniel is the host. The network bit is that constant part which always repeats itself. So how do you know the bit that belongs to the network and the bit that belongs to the host? The subnet mask will tell us. The subnet mask. So subnet mask is simply that number which tells you the number of bits that belong to the network. So supposing I write an IP address as in 172.16.3.17 and I bring /24. This /24 here is called the subnet mask, and it's telling us that out of the 32 bits address that we are seeing here, the first 24 bits belong to the network. The network bit is 24. So from that we can deduce the host bit ourselves. This is the network subnet mask. IP addresses are meaningless without subnet mask. So to stress the point again, the subnet mask is that number which will tell us the number of bits that belongs to the network, as we know that network bit plus host bit will give us 32. So let's take more examples. Supposing we have an address of 192.168.3.20/29. How many bits belong to the network and how many bits belong to the host? 29 says the first 29 bits belong to the network. So from this, we know that the host bit will be 3, because 29 plus 3 will give us 32, the total length of an IP address. What if you have another IP address of 10.50.3.178 and a /19? How many bits belong to the network and how many bits belong to the host? This /19 or the subnet mask is telling us that 19 bits belong to the network, and from our deduction the total length of an IP address is 32. So 19 plus a number will give us 32, and that number is 13. So the number of bits that belongs to the host is 13. You have to deduce it once you are given the subnet mask in the / notation. You should be able to deduce the number of bits that belongs to the host. Subnet masks are written in two formats. What we just saw is called the / notation. So subnet mask you can either write it in the / notation or the dotted notation, dotted or decimal notation. They are all accepted, but I prefer to write my IP addresses in the / notation. So if you have an IP address with a / notation of 24/24, how do you write the decimal equivalent of /24? It's simple. So let's move up here. Supposing this address is a /24. This is telling us that the first 24 bits belong to the network. The first 24 bits. This is 8 bits, another 8 bits, 16, and another 8 bit, 24. They all belong to the network. The rest from here up to here belongs to the host. What the subnet mask of 24 will do is it's going to mark 1 under every bit that belongs to the network. So all the 24 bits here are going to receive 1s under them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. That is what the subnet mask of /24 has done, marking 24 ones under every bit that belongs to the network. Then the subnet mask will mark 0s under every bit that belongs to the host. Having done this, let's convert everything back to decimal. So if you have all ones, it's 255. Dot all ones in the second octet here will give us 255. Dot all ones in the third octet will also give us 255, and all zeros will give us 0. So /24 in the dotted notation is 255.255.255 and .0. 255.255.255 and .0. This is called the dotted or the decimal notation. Then we have the / notation. They are all acceptable. /24 is the same as this. So as network engineers, we have to be very much abreast with how we can convert from the slash notation to the decimal notation and vice versa. So let's drill ourselves. Supposing you've been given an IP address and you are told that the address is a /27. How do you convert this /27 into the dotted notation? So let's use the same scenario here. This IP address is a /27. This means that the first 27 bits belong to the network. First 27 bits belong to the network. So every bit here is for the network 8, 16, 24, 25, 26, and 27. So everything from here up to here belongs to the network. Then that is for the host. Just 5 bits for the host. So what the subnet mask will do is to mark 1 under every bit that belongs to the network. So let's do it. 8 in this octet. All the 8 bits here belong to the network. So network bit and host bit adding up to 32. All the 8 bits here belong to the network. So 1, 2, 3, 4, 5, 6, 7, 8. In the second octet, everything belongs to the network. 1, 2, 3, 4, 5, 6, 7, 8. Also, the third octet has every bit that belonging to the network. 1, 2, 3, 4, 5, 6, 7, 8. And inside the fourth octet, 3 bits, 1, 2, 3, belong to the network. So you mark 1, 2, 3 in the fourth octet. Then you continue with 5 zeros. 1, 2, 3, 4, 5. Since the subnet mask will mark zeros and every bit that belong to the host. But after you've done it this way, then you convert every bit in an octet back to decimal. So all ones will give us 255.255.255, and converting everything here into decimal will give us 224. So /27 in the dotted or decimal notation is 255. That's 255. That's 255. That's 224. Let's take another example. So supposing we have a /19. An address has been written with a subnet mask of /19, and you've been asked to convert it into the decimal or dotted notation. What do? Simply mark 19 once. 1, 2, 3, 4, 5, 6, 7, 8 dot 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. You are done. Continue with 5 zeros in this octet to complete this octet, since we have 8 digits in every octet. So let's complete it with 5 zeros. All the zeros belong to the host portion because we are done with our 19 bits. So 1, 2, 3, 4, 5. The third octet is complete, and everything that belongs to the fourth octet, everything inside the fourth octet belongs to the host. So all the 8 bits, 1, 2, 3, 4, 5, 6, 7, 8. After that, let's convert everything octet by octet back to decimal. So right here we have 255.225.224. Converting everything in the third octet will give us 224, and everything here back to decimal with a 0. /19 is the same as 255.224 and .0. So we should be comfortable how to convert from decimal to dotted notation and vice versa. There is one thing that we must be conversant with that will help us in our conversion. So if you have all ones in an octet, as in this, every bit being 1, so 8 ones here. If the ones are 8, you have 255. What if the ones are 7? 1, 2, 3, 4, 5, 6, 7. If the ones are 7, you have 254. What if the ones are 6? 1, 2, 3, 4, 5, and 6. You have 252. If the ones are 5, as in this, you have 248. 4 ones will give you 240. 3 ones, 224. 2 ones will give us 192, and 1 1 1 1, like this. Turning all other bits to 0 will give us 128. Yeah. We must be very conversant with this, and that will help us in our converting from dotted notation to the slash notation. Let's see how we can use this to convert comfortably from dotted notation to the slash notation. So supposing you are given /22, an IP address is written with a /22 as the subnet mask, and you've been asked to convert it to the dotted notation. Instead of writing 22 ones, as in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. We are left with 2 zeros to top it up to complete this octet. Then 1, 2, 3, 4, 5, 6, 7, 8. All the ones are 8 here. So it's 255. In the second octet, all the ones are 8, 255. The ones here are 6, so 252, and dot 0. Instead of doing it this way, writing 8 ones this way, we can simply write 8 ones, dot 8 ones, dot 6 ones, and a 0. So 8 ones here, come and refer to your table, it's 255. 8 ones, 255. 6 ones, 252, and a 0 is always 0. That brings us to the end of this lesson. Please respect volume part 2. Thank you so much.